Um, Great. So our next speaker is Dr. Javeria Hashmi from Dalhousie University, Nova Scotia. Dr. Hashmi is an associate professor and holds a Canada Research Chair in Pain Research at Dalhousie University. She received her PhD from the University of Toronto and completed her postdoctoral fellowships at Harvard Medical School and Northwestern University. Dr. Hashmi is the director of Brain Networks and Neurophysiology Lab, which focuses on applying data-driven techniques to understand the role of brain activity and connectivity in pain perception and cognition. She aims to generate ideas and tools from brain imaging that can impact clinical measurement of chronic pain and other mental health disorders. And Dr. Hashmi is going to talk to us about interplay between prediction and sense datum in the brain. Please.
Hi, everyone. It's a pleasure to be here. So I am going to be talking about pain perception. I've been studying it for the past 21 years. So the model, like pain isn't like one of the, like I really enjoyed listening to the conversations this morning, and pain is one of like the qualia, the subjective experiences that are very hard to tackle for understanding what the brain is doing. And this is one of the reasons why I find this fascinating. It's subjective, it's incorrigible, it's intransitive. So there's no linear mapping between external events and the experience. And it also has clinical implications. So this is quite significant. 20% of human population is suffering with some kind of chronic pain. And we don't know what the reasons are, what's going on over there. And so they're like the work we do, we want to have an impact on the person who's walking down on the street. So that's another reason why this is interesting. And also for you guys, like who are interested in AI and stuff, like if you're working with machines that are interacting with the environment, I would assume that you would really consider pain and think about it, because in humans, children who are born with congenital insensitivity to pain, they do not live very long, because pain is the self-preservation, the system that ensures that we survive. It is the basic structure, like our threat sensitivity, our capacity to preserve ourselves has so many layers that extend not just from the physical, but all the way to the mental, to our schemas, to how we perceive the world, how we interact and give meaning to the world. So with regards to what we know, actually pain is quite an like least understood of perceptual phenomenon. I think we've been stuck with this idea of label lines, that there's some packets of information going up to the brain, and then we perceive some bell goes off in the brain and then we feel pain. It's not like that. It's a much more complex system. And so what we're doing in my lab is using the idea of Bayesian integration. And that's interesting because Bayesian integration is something that both you and I can understand. So what Bayesian integration is basically you're using some prior latent information, and then you're building predictions and matching the predictions to some sensory information. And then from that sensory information, like you build some confidence on whether your prediction is okay or not. And so it's an iterative process. So that's something machine learning and people who are doing your kind of work understand really well, and we also are interested in it. But one little thing about Bayesian integration that bothers me is that when we go in with model-based, computational modeling-based like ideas, we're not sure what the data actually looks like. And what I like to do is to look at data, and I like to build models or experimental models where we can actually parse out the phenomenon so that we can see a clear mapping of what's going on. So if we think about what how predictions may be working. The basic idea is that, oh, there's a match and information like what you're expecting and what you're getting, there's a match between that. So that's great. But when there's a mismatch, then the system will learn, the system will update itself. Now, in real world situations, is that true? And that's something that we see a lot in clinical situations where people have chronic pains. There's like nothing detectably wrong with their bodies. So if there's like update, how come they're not learning that there's nothing wrong with the body? Or there's placebo effects, there's phantom limb pains, all of these different phenomena. So there's like these non-linearities between experiences that we want to understand just experimentally, simple things that we can actually look at and believe. So if we talk about like just top down, what it is, you and I, we would think that there's some object outside of our body and that we have these 5 senses and this information is going to our brain and we perceive it veridically. So there's an actual object there that you and I are perceiving, but that's not what's happening. What we're doing is we're constantly searching for meaning. We're constantly detecting items that we already know about or have some kind of associative model to be able to explain. For example, you look at this chair. Those of you who are familiar with Van Gogh, the first thing that would come to your head would be, oh yeah, I've seen this before, this is Van Gogh. But for others who are like, say, for example, living in another part of the world and they've never seen it, it would be just a chair. So every object, even in your orientation columns, if you go all the way from looking at a speck, that's a dot. So there's a semantic meaning that we associate with it. If we see a line, we associate that with the word line. If we see like that getting more and more complex, we have some kind of all prior, some kind of latent that we will use to infer what that is. And that's an active process. So perception is not like a passive process, it's an active process, and we're constantly giving meaning to our surroundings. And our conceptual systems, our schemas, as we were talking about this morning, are almost like a cloud. It's like that lens through which we are perceiving and seeing the world. And we're very like stuck with the idea that, oh, this is concrete, this is something solid. But reality is that these concepts are built from these basic structures, and those basic structures are coming from our past experiences, from our brain development, who we are as an individual, who are the people we have interacted with. And so we're constantly using past memory information and then building predictions, and then sensing the world, building prediction, and then sensing the world. And that's how we move around. That's what we're really doing. And here's a simple experiment. There's so many fun illusions for top-down stuff, right? So as you can see over here, there's like these 2 letters, the cat. But if you look at the central letter, it's exactly the same. The meaning changes based on context. Similarly, for the ABC and the 12, 13, 14, the central item over there, the central character is exactly the same. So it's all about meaning. It's all about what we already know. And so this is a simple model. What is going on? Like, so the top-down information, it's not only predicting, it's also changing. It's also modulating our sense perception. And how that happens is that we have latent priors, we have like these, we're perceiving the cues from the environment, that evokes these latent priors, and depending on meaning, depending on the value, the associated motivations, we will pick up on certain things. And so the bottom-up sensory input will be either selectively be received, or as in the case of pain that you will see, you will actually actively modulate it, going back all the way down to the spinal cord. I'll show you that in a bit. So when we think about pain, just like any other sensory system, this is not a unidirectional ascending system. This is a looped system. Your primary sensory area is not in the brain. It's actually in the spinal dorsal horn. This is a bit controversial. Don't tell this to my colleagues. They'll be angry with me, but that's how I think about it. The spinal dorsal horn is the primary sensory area for pain. That's where we're receiving the first order neurons. And then that information is looped in several parts of the subcortical brain, and then it's being modulated. And when it, for example, the information it will, yeah, here we are. So the information that will go up the ascending pathways like this, and then it's also going to structures that are neuromodulating, and also the periaqueductal gray area, which is very interesting to us. I'm not talking too much about that, but that's the main area for our lab. And so that information is then blocking pain from getting into the brain. So what it does is it sends descending inhibition and blocks the activity in the dorsal horn. This has been demonstrated. So the idea here is that we have, just like in visual systems or auditory systems, we have feed forward and feedback systems that are controlling how much pain we feel or experience. And that's very important because we have to sometimes tolerate pain. And so we have to adaptively go through experiences. Sometimes they don't feel safe. Sometimes they feel dangerous, but we have to step into the unknown. And that stepping into the unknown requires us to feel a bit of pain. And that's where the system becomes like very sensitive. It tells you exactly how much is too much or where you need to stop. And that also depends on the individual, but we have like for our explore exploit systems, these very beautifully, intricately organized loops that are allowing us to be able to make safe decisions. Pain is the most important sense input for survival. Helen Keller didn't have vision and didn't have audition, and she did quite well, wrote beautiful poetry and everything. But children with congenital insensitivity to pain, they don't survive. So this is the most important system for us. And it's regulating a lot of our behaviors, more so than we actually address or think about, like how we perceive each other, how we interact with each other or with objects, is all like where there's this underlying tone of threat detection. And that is not happening in schemas necessarily. Our schemas, like self-report when it comes to pain, is not a good indicator of what is actually going on. So the schemas are faulty. It's really what's happening on the unconscious or the subconscious level in the brainstem, in the subcortical systems, that is controlling a lot of this type of behaviors that involve self-preservation. So what in our lab, we wanted to develop an experiment in which we could look at different levels of prediction error and then see how that influences people's pain ratings. And so for doing that, we give people cues. Oops, sorry. Oops. Yeah. So we give people cues. We show them when the incoming intensity is going to be 7%, the threat level is low, or we say it's going to be 90%. That produces a sense of fear in them, a sense of threat that this could be a strong pain stimulus. And then we would give them either a matched heat stimulus, like a heat pulse on their leg, or it will not be matched. And then after that, we're asking them to rate the pain. This is done inside a fMRI scanner. And what we were, so when we basically sort the pain ratings based on in like ascending order for cues. So the cues are going from 1 to 100. And when there's like a linear mapping between what they're expecting and what they're getting, so there's a match between and zero prediction error, then there's a linear trend as you would expect. So that's the schema that they've learned that, oh yeah, I see a number and the pain is equivalent to that. When the number goes up, I feel more pain, and so on. So this is what we're seeing with the gray line over here. In the orange line, what we did is, like for all of these events, the stimulus intensity was always 47 degrees. It's not changing. And we were pretty surprised to see this. That the pain ratings, they did update a bit, but it's a very modest effect. And if we map that now to different levels of prediction errors, we see that the update for the highest prediction error is not that drastic. And now we've run some new experiments, and we think what's going on is that we have a lot of cues, and so there's a lot of stochastic ground, like a lot of uncertainty in our model that is allowing this to happen, because we recently tested like just 2 Q levels. And when we do that, we see a update really quickly. So what that means is that in uncertain situations, people are defaulting to the expectation because they don't know what's happening. Their attention is biased more towards the cues and the schemas rather than the actual sense datum. And what's also interesting in this model is that if you look at the pain difference in the pain rating for the orange line, for example, over here, for the highest threat cues and the lowest threat cues, that is an indicator of how much they're like how drastically different their values are. It's an indicator of how much update they show and so on. So when we look at the different individuals are perceiving things very differently. A lot of them are like rating things more modestly in terms of differences between a high threat and a low threat. But there's also a group of individuals who are showing drastic effects. And so when we investigated whether this was related to the low threat or the high threat, as you can see that for one group, the differences are like increasing linearly for with the increase in the threat. But for the other group, there's like this amplification happening. It's almost like the higher cues, they're like perceived as stronger threats, and that's causing them to have this greater slope in the schema. And that's interesting because we think that has to do with brain networks, as I will talk about next. So this is my favorite topic, brain networks. So when we're like thinking about the brain, it's not like your kidney, okay? It's not like your heart either. It is a hairball, and it is very, very hard to study. What network analysis allows us to do is to look at things both at a very local level, and also we can look at interactions between different brain regions. So what that means is that we can either look at local connectivity, or we can look at activations, or we can look at connectivity that's happening on a global scale between networks. And what happens is that when we are doing resting state fMRI, we've been doing this for the past 10, 12 years now, there's a very consistent pattern that is emerging, that if you take tons and tons of data, the network tends to fall into 5 to 7 modules. We don't exactly know what each subnetwork is doing, but the consistency in the pattern indicates or suggests that this is something that we need to keep on pursuing and understanding, that there may be independent functions happening between these modules. But what I am most interested in is system segregation, like the balance between integration, like the connectivity on a local level and then connectivity on a global level, as I'll talk about. But just as a schematic of how we do this, we'll take the fMRI scan, so it will be multiple volumes. For example, we have 480 for resting state, and then we will apply a parcellation scheme. So the parcellation scheme can either be like something fixed, like the UO7, UO17. We have optimized the Harvard-Oxford Atlas. If anyone needs it, just let us know, we'll share that. And then from each parcel, we'll extract the signal from all of the voxels and average it to get one time series. And then we'll create like multiple time series for each person's brain. And then we'll basically correlate them with each other. You can use mutual information, but generally Pearson correlation works just fine. And then we are looking at the functional connectivity matrices, and then we can do all kinds of cute things with it. So the balance between segregation and integration in the brain is fascinating to me because it kind of encompasses a lot of the graph theory work that has been going around for a while, because what it's looking at is how brain subnetworks, they become independent and stop talking to each other or reduce their communication, versus what are the situations when they start interacting and integrating a lot. And this also makes sense to us because this is where we will be able to look at this interaction between top-down and bottom-up systems, between sense datum and prediction. And there's a lot, we're still early days. We don't really understand system segregation too well, but there's some exciting new things that have come out recently. So I've summarized them for you over here. So there's evidence now that shows that, and these are the reviews if you're interested, like work by McShine and this review article by Chan. Esposito has written a really good article about this. So higher segregation is associated with cognitive resilience, being able to carry out a mental task or an exercise, for example, like grit, for instance. And also, it may be associated with the cholinergic basal forebrain, like maybe parasympathetic, but we need to do more work, and we're working on it in the lab as well. And the higher integration, it is associated with attention, cognitive effort, memory. So, and it's also probably rooted in the sympathetic nervous system, but evidence is still gathering and there'll be a consensus soon. But this is the state of play for what we know about this metric per se. And so I showed you what the threat sensitivity was like, right? Like some individuals are very threat sensitive and they should show a more steeper curve. So we wanted to predict that. And this is work done by me and Veronica, who is now here at McGill. And so this is, we see, and we used different parcellations. We used 3 different parcellations, and we used also participant defined parcellations like Lewin based. And we also tested the metric at different thresholds. And what we found was that there is an association between system segregation and Q sensitivity. So the higher the Q sensitivity, more segregated the brain networks. And this was also associated with higher anxiety. And this result was significant for more coarser networks, but not with the refined version of YEO. This YEO parcellation has 2 resolutions, a 7 and a 17, which are nested. And so the results were specific to the 7 networks, and also with a completely different Harvard-Oxford parcellation. And yeah, so and also it wasn't significant for the subject-driven parcellations. I think it has to do with the resting state networks because they've been so well defined, and there's some kind of like more precise. They're allowing us to capture the information on a more consistent level across individuals, and that's why we're seeing that effect. Another interesting thing was that the system segregation, it was going down with age. So as we're getting older, the brains become more integrated. And in our data, we were seeing this effect more for the middle-aged individuals like myself, but not for the younger people. But then there are other studies that see a very linear effect, and we have a very small sample. So we will, like, I think that like the sample the data speaks for itself. Like we need bigger sample sizes to be able to give you more valid conclusions. So next I'm going to talk about system segregation with MEG data. Rhythms. Brain regions are interacting with each other through rhythms. And it's like the lingua franca of the brain. And if we do a Fourier transform on the broadband from the brain, we tend to generally get these different bands, as a lot of you guys already would know. But for information to be shared between distant parts of the brain, the slower frequencies are postulated to be more important, more meaningful, because of their phases. The phase synchrony can be more effectively entrained if you're looking at brain regions that are far apart with the slow frequencies. And so if for MEG, how we do this is that we look at amplitude fluctuations, right? So as the amplitude of a different band, say for example, beta or gamma, as it fluctuates over time, the envelope of that is a slower frequency. Interestingly, the frequencies match very well. It matched the resting state fMRI quite well. So we use that, and this was a development study. We looked at children from the age of 6 years to, I think we had 28-year-old adults. We had about 131 people. And I think there were 64 girls. Yeah, this was not work I did for my postdoc. And so basically the idea is very similar, except we extract the time series, band pass it to get separate information for each band. But then we also orthogonalize the phases, because as you guys probably already know, we're measuring at the sources, information gets mixed by the time it gets to the sources. So when we reverse infer it to the source, it gets mixed. So the functional connectivity maps, they are artifactual a lot of times for EEG and MEG. So this is a workaround, not perfect, but it's the best we could do at that time. And it's better than some of the other things that people are doing. So, and then we looked at the correlations between the different brain regions, created correlation maps, and then we did graph analysis. And what we find is that what we're seeing with resting state fMRI is a linear trend, right? Like system segregation is going down. But MEG allows us to look at different bands. And what we're seeing is that there's an opposite trend between gamma and beta. Now, for those of you who already know this, gamma, bottom up, beta, top down. And the networks are going in opposite directions, where the brain networks, they're becoming more integrated in the gamma, like they're becoming more distributed and spread out in the brain, and the beta is becoming more localized. And here we're looking at hubs, shrinking and growing hubs in the brain. And as you can see that it's just complementary further verification of what we have seen before, that for the beta, the information is becoming more localized, and these are the shrinking hubs. It's losing information from certain parts of the brain as the brain is developing. For the gamma, it is becoming more spread out, different parts of the brain. And we recently published a paper where we did some data mining using neurosynth to interpret what we had found. And what we're seeing is that the development of hubs in the gamma is happening in the dorsal and the ventral visual streams, in the motor, somatosensory, and motor cortices. Whereas for the beta, it's happening in the, as you would expect, in the attention networks, in the cognitive, like in the frontoparietal network, for example, which is very cognitive, very top down. And then we applied a machine learning algorithm, and this was a non-parametric multivariate regression model. We're using random forest, and we used the features for the graph features for the beta metrics, for the beta band, and then for the gamma band separately, and then we combine them to see if we're getting additional value. By combining them too, do we get better prediction? And the prediction intervals did look tighter when we do that. And then when we looked at the different features that contributed to the prediction, it was global and local efficiency. So the integration segregation type measures, they are the ones that were the most predictive of brain maturation. And so now I've talked about how system segregation may be important, like the balance between between segregation and integration is important for threat sensitivity, right? I've also talked about how it decreases with age, and that with MEG it is band specific. So now I'm going to talk about whether there may be a sympathetic component to this balance between integration and segregation. And so this was a paper that I worked on in collaboration with Keiju Olausen at NGH. And basically what we're seeing is that the functional connectivity, the strength of the functional connectivity was dropping. The global and local efficiency both were dropping. So the brain was losing its losing the synchrony, like the strengths of the synchrony. So, but this was only true for strength of synchrony, not the number of connections, which I find is interesting. There may be something there. So when we now look at degree distribution over here, we're sorting the nodes based on the most connections. We see a difference for the 3 different states only for the strength of connections. So the most connected nodes, the hubs, they are starting to become more weakly associated with each other. They're becoming more weakly connected with each other. Whereas that's not true for the number of connections. So it's not losing total number of connections, it's the strength. Now, what that means is, I don't know, but this is something that is the sort of thing that we should be thinking and working on. So next thing that's interesting. So I know it's like we're jumping from topic to topic over here. And honestly, there's like no cohesive summary that I can give you. Why? Because these are still early days, but there is a method to this madness. So hold on to that. So there are now a few papers, and the literature is growing on this, that system segregation predicts resilience in training. So for example, older adults who are undergoing CBT, so this is behavioral therapy, or another study showed that when individuals are put through an exercise training, people would appear for classes more and pay attention more if they have more system segregation. So the success, no, actually for these, they were showing that the success was dependent on baseline system segregation. So if your brain is more segregated, then the chances that you will be able to perform those tasks and be successful at the end was higher. So this is a study, fun story. This was a CIA study. This was funded, this was something that Sarah Lazar ran at MGH. And this was like where the army was trying to make smart people smarter. So they were taking all of these MIT recruits and putting them through MBSR, mindfulness-based stress reduction, and then they were looking at cognitive performance before and after. Don't ask me why, but I was only interested in the resilience component. I wanted to see whether there's differences across people in how they stick to the meditation exercise. I think what happens is that people who meditate, there's a lot of variation across them. Some people are able to sit. For others, it's like they can't sit for like even 2 seconds. And that is very fascinating. So we wanted to look at who are these individuals who are able to sit versus those who are not. And then the control group was the creative writing group. And what we found was that the metrics like clustering coefficients, local efficiency, which is like system segregation, sort of, not exactly, but sort of. And then, but we also looked at system segregation that also predicted how many classes they attended and how many practice assignments they did. The practice assignments were measured as timestamps because they were doing these online. So we had electronic data. And it was being mediated mostly by the meditation group. So the meditation group was the one that was already kind of predetermined to be able to meditate or not, depending on how segregated their brain networks were. But we also saw some effects for the creative writing group. And interestingly, when we mapped the clustering coefficients, which is a measure of how tightly a network is knit, at a local level, like how much is one node's neighbor talking to another neighbor. So it's like looking at triads, like triangles. So when we use that metric to get to the local level information, what we see is that the people who were meditating, they had higher clustering coefficients or more connectivity within the default mode network and the sensory network. And interestingly, for the creative writing group, it was the language processing network that was showing this behavior. So it may be that something that the networks are more integrated, more connected, and that's allowing or facilitating them to be able to carry on the exercise. But that's an interpretation, so we need to do more work. And this was another analysis that Marzi did for this paper, in which he wanted to see whether node level information can be used to predict who is going to be able to meditate versus who's not going to be able to meditate. And so she used, like we went in with the kitchen sink approach, because we're like, right now, at that stage, we were like, scoping out, like, do we want to use machine learning? What can it do? How effective is it? What kind of, whether we can get meaningful information out of it or not. So we used 4 different classifiers, and we wanted to see whether we can get a consensus on the accuracy. And I'm not super excited about small samples, although we have 70 subjects, but I think we need large samples for this kind of work. But at least as a proof of concept, we're starting to see that, yes, there's something there. And now we're more interested in figuring out what are the problems that actually need machine learning. Where do we, like, we don't have to just play with tools aimlessly. We need to identify the problem that actually requires these powerful tools and then apply them over there. And also that would mean that we need large data sets. So that's what we're now considering and focusing on. So to conclude, what I've said so far is that we have developed an experimental model that is usable for investigating the contribution of the predictions versus the sensory evidence and how in brain perception. This could be meaningful for understanding chronic pains and other clinical issues related with pain. And also it allows us to look at individual level sensitivity in a more principled way than just measuring, for example, pain threshold or pain tolerance. And so from that, we can go in and find out like which parts of the, like what is going on at the brain level, because we need to have enough behavioral data, like variance across individuals to be able to map that. And so we're seeing that a lot with this metric. So we're excited about that. And what we just showed you is that segregation is predicting the sensitivity. And if anyone is interested, I'm taking new students starting next September. And so what I would like to do with is to look at criticality and the entropy type measures in these networks and how that is playing a role in threat sensitivity in chronic pain patients and patients with fibromyalgia, and what is the role of insulin resistance, what is the role of the blood-brain barrier that is being affected by neuroinflammation. So these are the sort of future blue sky goals that we're working on. And also I just showed you that system segregation, it is decreasing with age, but when we look at band level information and with using MEG, then we get even more information where we see opposite patterns that we would not be able to see if we were just looking at only broadband. And that information is also showing us like a top-down, bottom-up systems developing and then coalescing into an adult version of what the networks are supposed to look like. And that we do have evidence that the noradrenergic tone may be important for maintaining this type of a balance between segregation and integration in the brain. These are my collaborators. This is my lab, and I'm going to leave you with this slide.
Hey, thank you so much for the great talk. We have time for one question. Yes.
My name is Matt. I'm curious, this is kind of like a high level question about subjectivity. Kind of, you alluded to qualia at the beginning, and I'm curious. So if I get like a bruise on my face, it doesn't really feel qualitatively differently to me than if I get one on my hand. And my knowledge of anatomy is not the best, so this might not make sense, but as far as I know, cranial nerves mediate pain on your face, right?
Mm-hmm.
And that wouldn't be, you mentioned that the dorsal horn is like what you would implicate the most. So I'm curious, if the peripheral feedback loops are different, why would it feel qualitatively the same? That's presumably something that's happening in my brain, right?
Good, very good question. So what your experience is going to look like is going to be very different from the person sitting next to you. That's the frustrating and the fun part about pain. Subjective experiences vary. For example, from the literature, what we know is that anything that is related to the face area, like the trigeminal system, is a stronger threat because this is the area that we protect most, right? So this is where we're like very sensitive, and the way we respond to stimuli through like the cervical system, through the trigeminal system is different from how it would be from the rest of the body. We like how Alan Watts talks about it, like, you know, how we perceive ourselves as if we're like a brain floating in a body, and this is like some kind of extension of the brain. But that's illusion of how we perceive things. The reality is that the body is a part of us. And that's another thing that I feel like with this model I want to pursue, to demonstrate and understand and explain the embodiment aspect of it, that we're not just brains floating around. We are embodied, and our bodies and being connected to our bodies is extremely important. And I say that because we're all on our phones all the time and spending so much time thinking. And that is affecting a lot of people's health. And I'm seeing that because I'm working with people with fibromyalgia. I'm working with people with chronic back pains. So these are some of the factors that contribute to bad health. And so we're becoming a very schema-driven, very cognitively oriented, very intellectually driven civilization. And we want to go to Mars. So we have a real paradox on our hands. And I think that the embodiment aspect is very important. Yeah.
Okay. Thank you so much. Thanks. Thank you all for being with us so far, and thank all the speakers for their great talks. We have 10 minutes break. Go get caffeinated. I know you all need it, and come back in 10 minutes at 4:05.